Hello guys, welcome to Learn Extra Live. We are on Physical Science for grade 12s. I hope all you grade 12s are ready and steady for such an awesome show, action-packed show. I hope that your day was also stunning, but not too stunning that you're too tired to join us now. So I hope that you kept a good balance so that you're ready for Physical Science. Today, Phil is finally back. I know that you guys have been missing him. How are you, Phil?
I'm great, thanks, and you, Kat?
Great, thank you. Please let us know what we'll be doing today.
Well, today we're dealing with electrochemical cells. We're stripping it right down to the basics, and we're going to try and see what the two types of electrochemical cells are and how they work.
Awesome, you guys heard that, right? So please jump onto Facebook, facebook.com/LearnExtra. Jump onto Twitter @LearnExtra. Join us on these platforms, guys. Please engage with us. There'll be lots of stuff happening on the page. There'll be stuff on After Earth, which I will be letting you know about that later on in the show. So fingers crossed everything goes well and I'm nice to you guys, and I will show you an awesome clip. I hope that you guys are ready for this awesome show. Ask questions on the page, guys. We're here for you. Hey, Phil.
Absolutely, Kat.
Take it away.
All right, well, as I said today, we're dealing with electrochemical cells. Now, guys, I'm a big fan of taking apart these big, long, complicated words and trying to figure out what they mean even before we get into the section. So even if you look at the word electrochemical cells, this is something to do with electricity and chemistry, or electricity and chemicals. So what we're going to do is we're going to try to see how chemicals can give us electricity, or how we can use electricity to get some chemicals. We're going to be talking about some energy. We're going to be dealing with a little bit of redox. I know a lot of you are a little bit anxious about your redox. I'm going to try and help you and make things a little bit easier. And if you watch very closely, between when the ad breaks, what we're going to be doing is we're actually going to be constructing our very own battery out of some common household materials. I'm going to show you how you can do this at home, and it's pretty awesome. So let's jump right into it. Let's start dealing with electrochemical cells. Let's first find out what we're going to be doing. And the first thing that we're going to do is we're going to differentiate between two different types of electrochemical cells. And that's very important. You've got to know what you're dealing with before you can understand how to deal with it. There we go. And then we're going to apply some knowledge to reduction and oxidation. I'm going to show you how to choose off the table, how to write out these chemical reactions, and how to choose the right ones. So guys, watch very carefully, especially if you're having problems with some redox. Grade 11s, if you've managed to watch this show, because it's really nice to study ahead, you can actually get some gain from this as well. But grade 12s, guys, this is awesome revision when you're dealing with reduction and oxidation. We'll deal with some of the more difficult words, and we'll try and figure out what's going on there. And then finally, we're going to use some electrochemical cells to make electricity and some new chemicals. That's what I'm particularly excited about. We're going to deal with some new chemicals. We're going to try to see where the energy is moving. Is it moving into the chemicals or out of the chemicals? And how do we actually see what's going on? Okay, so let's start off with our first point there. Let's actually differentiate the two different types of electrochemical cells. And here we are. There's two major categories, and I'm going to show you how they're differentiated from each other. Now, galvanic cells. Now, galvanic cells, a lot of people are kind of saying, well, you know, how do I tell a galvanic from an electrolytic cell? There's some very important differences, and it's mostly to do with what they do, what turns into what. And here we go. Let's just highlight the important pieces. And guys, just a reminder, the notes are on the page. Get those notes, because what I've done is I've actually included most of these comments in those notes. So it's going to save you a lot of writing time, so you're not going to be making these furious notes, and you're actually going to be watching the awesome experiments and making some additional notes to those. So there we go. Galvanic cells. These are the really important ones. These change chemical potential energy. You might say, what is chemical potential energy? Well, guys, if you're busy snacking down on something really delicious, you are eating your own very own chemical potential energy. You are investing energy inside your body, into your cells. Chemical potential energy are chemicals which have got a lot of stored energy inside them. Now, we're going to turn some chemicals which have got stored energy into electrical energy. Now, you might say, oh, you know, why am I learning this? Why is my teacher torturing me with this redox stuff? Why should I do it? Well, guys, if you're reading your notes, or if you've played around with your cell phone in the last 5 minutes, and if you're a matric, I know that you have, you're tempted, you're just playing around with that cell phone. Okay, now these chemical reactions at the moment are busy entertaining you guys. Your cell phone batteries. This is how those batteries actually work. So matrix, if you haven't done batteries yet, This is how it works. Galvanic cells actually power my mobile devices, my tablets, my mobiles, my laptops, anything is powered by chemicals which make electricity, and that's pretty awesome.
That is pretty awesome.
And right now, Kat's busy looking at a laptop which is having one of these batteries inside, so it's fantastic. You're actually seeing the stuff in action.
Yeah.
So please, off the cell phones, watch the show.
Well, they can use their cell phones only for Facebook and then put them away. And then
Well,
Facebook
absolutely.
And then
If
put
they're
them away.
following on Facebook, there is an exception. Okay, guys, asking questions,
Yes.
sharing ideas. Okay, well, let's get into the other type as well. Now, you might say, okay, well, I really like galvanic cells because they power my cell phone. I love my cell phone. It puts me in touch with Learn Extra. How do I use electrolytic cells? Well, let's first figure out what they are. Now, these change electrical energy into chemical potential energy. Now, you might say, okay, well, why would I want to do this? Now, here's the really amazing thing about electrolytic cells. Electrolytic cells have the potential to make new chemicals. So now, the one I changed chemicals into electricity. Let's just extend this a little bit. Now, galvanic cells use chemicals to make electricity. Electrolytic cells use electricity to make chemicals. Now, you might say, well, why do I need electrolytic cells? Well, guys, you can't use your cell phone forever. That little cell inside your cell phone is designed to undergo both of these reactions. When you're playing on your cell phone, galvanic cell. When you're charging your cell phone, it's an electrolytic cell. What's happening is you're plugging it into the charger, and the electrical energy is coming out of your charger, out of the wall, and into your cell phone and charging up that battery. So under that stage, when you're charging your cell phone, it's an electrolytic cell. When you're using it, galvanic cell. So let's try to figure out how these things actually work. And I know matrics have got a lot of anxiety when it comes to this section, and you really don't need to. So again, galvanic is when I change chemical potential energy into electrical. Electrolytic cells are when I change electricity into new chemicals, or I store it as chemical potential energy. And if we get time a little bit later on the show, I can actually show you that chemical potential energy that's been stored in some chemicals, and I'm really excited to do that. Okay, so now let's start off with the first one. Let's start off with our galvanic cells. So once again, let's just highlight that important difference. I start off with chemical potential energy. Okay, so chemical potential energy, remember, are chemicals with a large amount of stored energy. Now, here's the problem. That chemical potential needs to come from somewhere. Those chemicals still need to be made. So this is not free energy. This is not energy which I just get out of thin air. That chemical potential energy is usually put there by a factory or some manufacturing plant which needed to put in the energy in the first place. So please, if you want to make sure that you're covering all your bases, that chemical potential energy comes from somewhere. Now, what does it change into? Well, we've got some chemical reactions which somehow change chemical potential into electrical energy. So that's the electricity which is powering that big, beautiful laptop screen, or that tablet, or that cell phone. So I'm going from that chemical potential into electrical energy. Now, here's what you'll need if you want to make yourself a successful galvanic cell. Now, over here, this is a very basic form of doing it. I need two metals. Now, these two metals need to have something. Now, this is going to start confusing a couple of people. It says, with different oxidizing or reducing ability. Let's just put a slash in there. Okay, so different oxidizing or reducing ability. It depends on which side of the table you're looking at. So how do I decide that? Well, they're in different places on the table. So it's different oxidizing or reducing ability. Now, let me just strip that down to the bare basic idea. Now, these are two metals which have different desires for electrons. They want electrons different amounts to each other. So one really doesn't want them, one really wants them. And what they're going to do is they're going to give each other electrons. There needs to be a difference in how much they want those electrons. So what we're going to do is we're going to take two metals and use them to create electricity. And then the very last one. This is quite important. I need something which is called an electrolyte. Now, an electrolyte, if you want to put it down to its simplest form, is a conductive liquid with ions in it. Now, an electrolyte can be anything, and you might have heard about this term in some adverts for some sport drinks or anything like that. My body needs electrolytes because my body is filled with electrochemical reactions. In fact, all these nerve impulses rushing around inside my brain are electrochemical reactions. They are galvanic reactions, where an electrolyte of sodium and potassium are swapping places and allowing my nerves to conduct. So if you do life sciences, you're actually doing redox chemistry inside that axon of the nerve. And this is because I need electrolytes. So the electrolytes which I take in with my food are sodium ions and potassium ions, and those are conductive ions. They allow my nerves to work. In fact, you couldn't see this picture without an electrolyte inside the back of your eye and inside your brain and rushing all those chemicals. So here we are. Let's just revise what we need. We need those two metals. They need different oxidizing and reducing ability, and I need an electrolyte, which again is a conductive ionic liquid. So usually it's a solution. So let's just get some ideas on what we might actually need here. Let's take perhaps two metals. Now the most commonly asked metals over here, and you'll see this in your textbook a lot, are zinc and copper. Now zinc and copper are pretty nice because they're nice and available. They have different oxidizing and reducing abilities. I'll show you in a moment how to do that. And I need some sort of electrolyte. Now this electrolyte can take many different forms. And in fact, I'll show you a little bit later that you can actually make an electrolyte out of your body. And our electrolyte of choice, a little bit later on in the show, and this is going to come up after this ad break, is actually going to be some lemon juice. Now the lemon juice is going to be inside a fresh lemon. We're actually going to make a lemon into a battery, and that electrolyte is filled with an acid, which gives us a little bit of H+. So there's my ions, and they are in solution. So that is aqueous. So all we need is two metals and something in between, which is quite conductive. So I hope that you can see that a galvanic cell is something which is chemical potential to electrical energy. Now, why would they make electricity? Why would they swap electrons? Well, it's to do with how much zinc and copper like electrons or want electrons or even want to give away electrons. Because remember that metals really like to give away electrons because metals want to be positive to complete their outer energy levels. Metals like to give away electrons. Now, it's all a competition. Does zinc want to give away the electrons or does copper want to give the electrons away? We don't actually know. So what we've got to be able to do is we've got to work with something called a standard reduction potential table. So what I'm going to do is I'm just going to flip that up on the board for a moment. And there we are. We're actually going to deal with this a little bit later with our electrolytic cells. Guys, just to plan ahead, I want you to have this table in front of you. Now, if you're looking through your old exam tables, it's right at the back of your exams. It's called Table 4B. I'm using the second one. It's the one with lithium on top. Now, I've just cut out a small section of this because this actually deals with chemicals which I'm going to be talking about, especially when we deal with electrolytic and electrochemical cells. I'm going to show you how all these chemical reactions take place, how to select the correct ion, and to go through all the steps. So now, just to highlight what we're doing, what we're actually doing is we're competing zinc with some copper. And what we've got here is various different reactions which can actually happen. And you might notice that it's actually really, really difficult to try and select the correct ions. So I'm going to show you exactly how to do that as we move on. I've just cut off a tiny little piece of this to show you. Okay, so guys, what we're going to do now is we're going to go back to that reaction and we're going to make some predictions. So now, what I need is something that looks a little bit like this. Now, I'm not sure why it's done that, but what we'll actually find is that zinc is the one which likes to give away electrons and copper is the one which likes to gain electrons. You might see this in a lot of your textbooks. This is the basic zinc-copper cell. Now, how on earth do I know that zinc changes from zinc into zinc 2+ and copper 2+ into copper metal? So what I'm actually going to do is I'm going to investigate if this actually happens, how do I actually set up one of these cells, and how do I come up with all of these labels for electrodes and electron movement and all of this fancy stuff? How do I, for instance, predict that zinc is going to be the one to lose electrons and copper is going to be the one to gain? Now, just a little bit of redox revision from your grade 11. Let's try and identify these two reactions before we go on. Zinc, in this reaction, as it's written down, goes from zinc to zinc 2+ plus 2 electrons. That means that zinc is undergoing oxidation. What about copper? Copper is changing from copper 2+ into copper metal. Now, if you remember, the gain of electrons is called reduction. Now, if you're a little bit rusty on how I actually managed to do that, there's a really nice way of doing this. So you write out the word oil rig. And the way that I use this, I start out with the word oil. So let's actually go through this step by step. So I say oxidation is loss. So oxidation is loss of electrons. What about the other word, rig? Reduction is gain. It's as easy as that. If you're trying to figure out what's going on in terms of electrons, oxidation is loss, so that's oil. Reduction is gain, and that's my reduction reaction. The question is, how do I actually see if oxidation or reduction is happening by the electrons? Well, it's all to do with where the electrons actually are. So if I look at this first reaction, I see that the electrons are on the right-hand side. Now that's pretty important, that the electrons are products. They are coming out. That means that electrons are being made. Now please be careful. A lot of people get really confused by this plus. They say plus means add. No. In chemistry, when you're looking at chemical equations, plus means and. So let's read this chemical equation in words. Zinc goes to form zinc 2 plus and 2 electrons. That means that the electrons came away from the zinc. They were lost by that zinc. What about my copper electrode? My copper electrode said, okay, well, copper 2 plus and 2 electrons. There they are. They're on the left-hand side. Did the electrons come out? No. I made copper metal as a product. That means that the electrons were gained. Okay, so now I've got my oxidation reaction. I've got my reduction reaction. And what we're going to do, I think we're just in time for this. Okay? What we're going to do is, after this ad break, I'm going to show you how zinc and copper can make electricity. We're going to use a lemon, then we're going to use some half cells, and we're going to try and figure out what some of these labels actually mean. I think it's time for an ad break, eh? What do you think?
I think so, Phil.
These guys need a bit of a breather.
I think so, but after the break, we have such awesome stuff coming along. So take your breather really quickly and join us right after. Thank you to Macmillan for sponsoring such an awesome show. I'm really excited to show you guys what I have in store. So please, please, please join us after the break because it's going to be awesome. See you just now. Welcome back, Mindsetters. As I said earlier, we have some awesome big news coming up, and that is After Earth, guys. After Earth, that movie, you know about that movie with Will Smith and Jaden Smith, the really awesome father and son duo? Yes, we will be showing you the trailer to that, guys. Really important. You need to watch this afterwards. I'm going to tell you more about it, and I'm going to tell you how you can enter the competition where you can stand a chance to win 2 tickets, guys. That's 2 tickets for you and a friend to go watch this movie. So watch the trailer and maybe you'll get some inspiration there of how to look after our Earth, number one, and also obviously some inspiration from Will Smith and Jaden Smith. Watch the trailer, guys. See you now. Wasn't that absolutely awesome, guys? Of course, you can stand a chance to win 2 tickets, as I've just mentioned. But before that, you need to actually jump onto www.learnextra.co.za/After Earth. The link is on the page. I can see it. And then you need to enter a competition. What you need. Now what you need. You need a code, right? You need a password, and you need it from me. And I'm going to give it to you in a few seconds. Before I give it to you, I am going to be announcing winners who have won from yesterday's show, so that I just want you guys to get inspired to enter the competition, basically. You guys really need to enter it. I want to join you guys to watch Will Smith and Jaden Smith, even if that's all I want to join you for. So make sure that you enter that competition. The password and the keyword, whatever you want to call it, is diversity. Diversity, guys. So as you enter that competition, type in diversity and you can stand a chance to win. Keep your eyes posted, glued, whatever it takes on Facebook for the next 3 weeks. This competition is only available if you're in South Africa. As I've said to the grade 10s and the grade 11s, if you're not in South Africa, please jog over here or fly or take a ship, whatever means you need to get here. Enter that competition, watch the movie, and then go back home, because it is really going down here, guys. Of course, the competition does close at 12 p.m. tonight, so make sure that you enter it in the next few hours. Now, the winners from yesterday's show. Number 1, Liam, well, not number 1, number 2, number 3, but you know what I mean. There's 3 winners, right? So that's Liam Cosgrove, Apiwe Makatini, and Raymondi Van Deventer. I'll say that again. That's Liam Cosgrove, Apiwe Makatini, and Raymondi Van Deventer. Guys, just double check on the Facebook page. Also send us your details if you are one of these three. Well done to you guys. If you don't have a friend, remember Phil and I are here to join you to watch the movie because we are really, really excited to see it. It comes out on the 7th of June. Phil, can you believe it?
That's amazing.
I know, hey, it's soon and I'm really excited.
Oof.
Over to you.
Well, what we're going to do is we're going to carry on the excitement. We're going to start making some really cool stuff. So what I've got in front of me is all the equipment that I actually need to make my very own battery. We're going to change some chemicals into some electricity. Now, I want you guys to get a little bit closer. So what I'm going to do is I'm going to show you some of the chemicals that I actually need. Remember what I told you before the break? I need 2 different metals and I need an electrolyte. Now, my electrolyte is coming in the form of just the simple lemon. Now, lemons themselves are full of really nice acid, and that's why they taste so sour. What I'm going to do is I'm going to insert my 2 different metals. This silvery one, this is called zinc. So I don't know how many of you guys have actually seen zinc metal. It's not very common around. It's usually used as a part of something else, and I'm going to stick it right inside there. Now, the other metal which I'm going to use is some copper. Most of you have seen copper before because it's part of the 5-cent coins, and you actually see it quite a lot around the house, and it's what I make wires out of. So I'm just going to insert that on the other side. Now, what I've got to detect the electricity or find out if there's electricity being made is this voltmeter over here. Now, this voltmeter is incredibly sensitive. It's so sensitive it can actually pick up my nerve impulses. So what we're going to do is we're actually going to take this voltmeter and we're going to try and see if there's electricity coming from our battery made out of a lemon. So if I start to attach first the zinc, then the copper, we can actually see some of the electricity flowing, and we can see those numbers changing and jumping around. Let's just make sure that we're getting a positive voltage there. There we go. All right, and you can actually see how much voltage is coming off this battery. And let's just make sure that we're nicely connected and not connected to each other. There we go. You can see that that voltage is starting to stabilize. I'm getting nearly a volt out of this. So obviously, if you need to power a cell phone or something, you're going to need about 5 or 6 different lemons and quite a few of them. So this lemon is actually producing around about 0.9 volts, just from the difference in the desire for electrons between the zinc and the copper. Now what you'll find is that zinc doesn't really like electrons all that much. Copper itself doesn't really mind having those extra electrons. So zinc wants to give away electrons so badly that it can actually send electrons around an outside circuit onto this copper. Now, something else that's particularly interesting is that these metals are chemically changed by the chemical reaction inside. Now, if you take out these metals again, you'll actually start to notice that there's a chemical change on the surface of here. Now, if you get really nice and close, you can actually see that there's 2 parts. This copper looks super, super clean. And this is one of the ways that some of those cleaning products actually work. They use redox chemistry to clean the surface of the metal. Now, just a bit of a cleaning tip for at home. If you're trying to clean copper or silver, what you can actually do is you can take aluminium foil and some lemon juice and you can rub on that surface. And what you'll find is that your silver or copper will be very nicely cleaned. But now there's an electrochemical reason why silver and copper can be cleaned by those reagents. What about this other metal? Now, you can actually start to see that this other metal has started corroding. There's 2 parts to this again. The zinc itself has actually started dissolving. You can actually start to see this black substance on the top here. That's the zinc, which is actually starting to dissolve into this lemon. It's actually reacting and dissolving. If I left this long enough, what we'd find is that the lemon itself would disappear. It would oxidize completely and vanish. So there we have it. We've got these 2 different metals, which like electrons, different amounts. But now, lemons are not a very exact way of doing electrochemistry. So what we like to do is actually separate them into 2 half cells. So let's try to see if we can generate electricity with these 2 things and the full equipment, which is talking about that cell. Now let me just introduce what a cell is. A cell is made up of 2 halves, one where oxidation will take place, one where reduction will take place. Before the break, I told you that zinc is where oxidation took place and copper is where the reduction took place. Now you might notice this really strange piece of equipment which is connecting them. I've got 2 cotton wool plugs right in the end over here, and I hope that you can see them. These cotton wool plugs stop this liquid from coming out here, and you can actually see that I can hold it upside down without the liquid leaking out. Now this is filled with an electrolyte. This is filled with KNO3. That's potassium nitrate. The reason I really like using potassium nitrate for this part in the middle that continues all the electrolytes is because all potassium salts are soluble and all nitrates are soluble. Now, what are these liquids inside here? Well, if you were listening really carefully, what I needed was my two metals and I needed electrolytes. Now, what I've used for electrolytes are some salts. Now, just to show you some of the salts that I've used some blue copper sulfate, and I'm actually going to open this up and show you what's going on inside there. Blue copper sulfate is a salt over there. Now, these salts are dissolved inside this liquid. So I've taken my copper sulfate and put it into the copper electrode compartment, or the copper half cell. The reason I call it as half cell is because it's half of the cell. Now, what about the other side? Just to keep things very, very simple, I've used zinc sulfate. Sounds very familiar. That sounds like a salt. I've also dissolved that inside this. Now let's actually try to see if we can generate electricity using my two half cells. I've got my zinc, which likes to oxidize. I've got my copper, which likes to reduce. Now let's try to see if we can generate some voltage. Now let's look at my voltmeter again, and let's see if we get some electricity flowing out of this. Well, what you can actually see is that we're generating almost an entire volt. Let's try to see if we leave it to stabilize. There we go. What you'll actually notice is that you're generating quite a lot of voltage. And this is how the battery inside your cell phone is actually working. There we go. Once it's going, it's generating well over a volt. Now, if you're fairly far along with your redox chemistry, you'll actually know that there's a way to calculate or predict how much voltage is inside here. I've made sure that these solutions are 1 mole per decimeter cubed in concentration. They aren't quite 25 degrees Celsius, which is the standard temperature for them, but there's a way to calculate their voltage. Now, their voltage depends on both concentration and temperature if you're taking notes on redox chemistry. So let's just revise what was going on here. There are two compartments over here. I've got one compartment with zinc metal, my zinc electrode, and this solution. This solution is made up of a salt which is dissolved in water. On this side, I had copper ions in the form of copper sulfate, and then I had my copper metal. Now, what we had to do to complete the circuit was include something to sense how much voltage was being made. So there we go. I've attached my voltmeter, and you can actually see the voltage is rising over there. I'm producing electricity as we speak. We can see that the voltmeter is actually picking these up, and the voltage is changing very, very slightly. Now, that might be a change in concentration, or it might be a change in temperature. There's several factors which can affect this, but this is roughly 1 volt. Now, what you'll find is that the electrons are flowing out of my zinc and into my copper. So what I'm going to do now is I'm going to leave my lemon battery, and I'm going to leave this. And what we're going to do is we're going to try to see if the metal itself actually makes a difference. Now, earlier on, I was just playing around inside the studio, and I wanted to see what the effect would be if I changed one of the metals. So what I've done is I've now still got my zinc electrode. Let's put my zinc back in the lemon battery. What I've got over here is actually a strip of lead. Now, instead of zinc and copper, now I've got zinc and lead. Now, remember that we generated around about 0.9 volts using zinc and copper. Now, something quite nice to notice is that the type of metal changes things quite a lot. Let's look at our voltage. Now, you can see that zinc and lead are not as effective at making a battery. That's because zinc and lead have actually got very similar likings for electrons, much more similar than zinc and copper. So you can see that changing the metal itself is an important factor as well in the voltage which a battery produces. So a zinc-lead battery wouldn't be very effective. A zinc-copper battery, almost twice as effective at generating voltage. Very, very nice. So what I'm going to do is I'm just going to quickly pass back to Kat and see what's going on the Facebook page while I take up my post, and then we're going to explain.
Sure.
How's it going on the page?
It's going really, really well, Phil. I think people are more excited about After Earth than anything that has ever hit this page. So I want to urge you guys even more to jump onto that mindset page and actually enter the competition, guys, so that you can stand a chance to win those tickets. Most of you are like, oh, wait, where do I go? Where do I go? Don't worry, don't panic. It's on the page. And to the winners of today, congratulations. You guys are going to watch After Earth. Isn't that awesome? Well done. Over to you.
Thanks so much, Kat. Amazing. I'm excited about that movie. Guys, get on the page. Win the tickets. Really?
Please.
It's so easy. Okay, and what, diversity was a password?
Diversity
We
was
even
the
give away the answers.
I know, right?
Amazing.
We're awesome.
Okay. Well, what we're going to do now is we're going to try to figure out what was going on inside that lemon battery, that crazy thing that was just like a lemon, a fruit that made electricity. I mean, that blows my mind that you can just stick something in one side and something in the other side and you make electricity. 5 of those will actually keep your cell phone on. So if you stack out in the wilderness without electricity and you've got some lemons and you've got some zinc, you know what to do. Okay, well, guys, actually, it's any 2 different metals. Now, the copper inside a 5-cent coin will work as well. Aluminium foil can replace the zinc. And what you'll find that aluminium foil is not the best, but it does actually produce some sort of voltage. You might need a lot of batteries to power your cell phone, though.
Yeah, I know.
So if you're experimenting, just be careful and don't use all your mom's lemons.
She'll be upset.
She will be upset. Okay, well, let's get back into the chemistry. Let's try and figure out how we know what's going on inside those cells. How did I know that zinc was going to be oxidized and copper reduced? Well, guys, if you were listening a little bit earlier, I need you to have an expanded view of your redox table. So what I'm going to do is I'm just going to write out the important parts. Now, there's several things which went into those half cells, and I want you to look for these. I had zinc. I had zinc sulfate. And in the other side, I had copper, and I had copper sulfate. Now, guys, please remember that these salts were aqueous. They were dissolved. So that means that zinc splits up into 2 parts. You will not find zinc sulfate anywhere on your redox table. You will find zinc 2+, and you will find sulfate, SO4 2-. What about copper sulfate? It does exactly the same thing. Nice and simple. We get the copper 2+ ion, and we get a sulfate ion. Okay, guys, so what's the deal? When you start circling things on your table, where do we find all these things? Now, I'm going to give you a quick guide on how to find these. You're going to circle only the chemical which you have. Now, please, guys, that zinc and that zinc are not the same thing. That's a metal, that's an ion. This was nice and shiny, this was a salt. Guys, they are completely different to each other. But if you have all 6 of these, I want you to get on that redox table and go and circle them, but don't circle the whole reaction. What do I mean? Just circle the thing which you have. Just circle the zinc or the zinc 2+ or the SO4 2-. Now, there's some confusing things which you'll find on that table. So once you've circled all the zinc 2+, the sulfate, the copper, and the copper 2+, I'll show you how to pick the best one. So this is the first step. Figure out what you've got, guys. Then, this is where you go. So now, if you did this very, very carefully, what you'd find is that there was zinc up on the top right. There's zinc 2+ on this side. And if you start taking a look a little bit further down the table, you'll find sulfate somewhere in the middle. And you'll find copper 2+. Now, here's the really confusing thing, is that on some tables, you'll actually find copper 2+ in 2 places. Now, this is so weird. How do I deal with this? How do I actually find out which one is the correct one? So if this is your table, and you're trying to figure out what's going on in here, I want you to actually go and physically circle, circle, circle. This might seem like a really silly exercise, but what I'm going to do now is I'm going to show you how to do redox off your table, okay? Now, Matrix, if you know how to do this, bear with me and confirm what you know, because there's a lot of people who are doing this incorrectly. Please, first mistake, rookie error, is to circle the entire reaction. Don't do that. Just circle. They're called chemical species. Just like animal species, these are my chemical species. So what we're going to do now is we're going to figure out which one we've got and which one is the best one for the job. So on the left here, if you look very carefully, your examiners have been very, very careful to put some arrows there for you. The arrows are the key, guys. The arrows actually tell me which one to choose. So on the left, I've got 4 things to choose from. Which one should I choose? This is easy, guys. Look down on the left. The arrow actually points in the right direction. So let's do this. So the correct one is right down at the bottom. This is the winner of the competition. So there we go. So we've got copper 2+. On the right-hand side, who's going to win? Well, look at the arrow, guys. The arrow tells you which one. The arrow points up on the right-hand side. There we go. Zinc's winning this one. Now I know which ones are my reactants. All I've got to do is circle what I've got and then pick the best one. And that's how we do it. Look at the arrow, guys. They're there for a reason. Now,
Before you go on, Phil, can we take a bit of a break there?
We can actually. Okay, guys, I'm just getting so wrapped up in this. I love this chemistry.
I can tell, and I think they are as well. But
Okay.
just for our safety, I think we should.
Absolutely.
So, guys, a quick break. Run to the bathroom, run to get a glass of water, and we'll see you right after this. Welcome back, Mindsetters. What an awesome show it's been so far. You guys have learned a lot. I know I can see on the page how busy it is. Guys, if your friends haven't yet, I know Emmanuel just said, hey, I've just joined the page a few minutes ago. Welcome, Emmanuel. And if you have friends like Emmanuel who are not on the page yet, please urge them to join us, guys. I can't believe that we're almost at, what is it now, 50,000. Wow, that's
Amazing.
awesome, hey Phil.
That is
50,000 likes
incredible.
on the page. I know, I think we can get more
Absolutely, guys. Tell your friends.
Tell your
Tell
friends.
everyone. Tell your parents.
as well.
Tell your younger brothers and sisters
I
because they're
know.
going to be matric soon.
Yes, they are. And people were even saying, oh my word, why do we have to go to school if Mindset Learn Extra Live is going to be here for us all the way? I was like, I think it's just to pass the time during the day until we come on at 4. What do you think?
Absolutely, guys. You got to get the groundwork in there and then
Yeah.
then tune in.
Exactly.
Well, guys, let's just finish off what we were doing here. Remember before the break, I said circle your reactants and then choose the best one. Look at the arrows to choose the best one. Now, here's the trick. What I have to do is I have to start from one side and then work my way across the other side. So let's just do this in a different color. So now, let's say I've chosen my copper 2+. The only way to go is across, and that's the way that I write this reaction. So it's from copper 2+ across to that side. On this other side, what about zinc? If I've chosen zinc as my chosen reactant, this is the chosen one, then what I'm going to do is I'm going to write it starting from my zinc and going across. Guys, that's how I figured out that zinc was my reactant, copper 2+ was my reactant. But what about the sulfate? The sulfate itself was just a spectator. It was just watching. It wasn't winning any prizes. Okay, sulfate didn't enter our competition, so it just had to watch. Okay, so now what's happening over here? I've got my zinc and my copper reacting in this beautiful cell. Now, what's happening inside this cell is that oxidation was happening at the zinc electrode, reduction at the copper. Guys, please, 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 these are terms which confuse a lot of people. Now, zinc is where the oxidation takes place. So there we go. Let's make sure that we emphasize that this is oxidation. As a result of this, I call that the anode. Now, copper is where reduction takes place, and therefore that is called the cathode. Guys, please don't listen to anyone that tells you that anode is always plus or minus, or cathode is always plus or minus. They are reduction and oxidation terms. Anode, oxidation, cathode, reduction. Now, there is a way to remember this. My matrix like this. Red cat. So if you think about the red cat, you'll know that reduction takes place at the cathode. There we go. Red cat is the way to remember this. Very, very easy. And obviously then oxidation will be at the anode. Okay, now we've got a little bit of quick time. What we're going to do is we're going to take a short look at electrolytic cells. We're going to change electrical energy into chemical potential energy. What do we need? Well, once again, we need 2 electrodes. Now, here's the thing which makes an electrolytic cell important. I need a voltage across them. I need a source of electrical energy. Then, I need the electrolyte. Now, the electrolyte is where the chemicals are actually going to come from. So what I've done is I'm going to be splitting water up into hydrogen and oxygen. Now, we'll see if that works. Now, what I'm going to do is I'm going to take H2O and a little bit of acid, and we're actually going to try and split water. We're going to try to see if we can release the chemical potential energy. So let's try and figure out what we've got over here. So here we go. So now I'm splitting water. So how does one use electricity to split elements from compounds? Here it is. At the positive electrode, what you'll notice is that H+, this H+, I'm going to supply in the form of an acid, and that's H2SO4. Remember that sulfate's a good spectator. That's why I like using it. So H2 is going to be the product of there. I should get nice hydrogen gas coming off there. At the other electrode, now this one wasn't copper, so let's actually correct that. Now what I've done is I've actually used lead as an electrode because the copper would be eaten. So what I've done is I've swapped that for a lead electrode, and the other product over there is going to be oxygen. Now the really cool thing about this is if I make hydrogen and oxygen together, they actually make quite an explosive mixture. So hopefully I don't blow up the studio. I know that cat's been a little bit like, what's going on here? So I'm going to make some H2 and I'm going to make some O2, and we're going to try split these apart. And what I'm going to do is I'm going to allow you to see that there's chemical potential energy actually invested inside them. So what I'm going to ask you to do is to come along with me. We're actually going to move along to our experiment, which is set up over here, and hopefully things work out. So let's move along.
Let's move along. I'm excited to see this one.
Okay, so now what is the important bits? I've got a positive and a negative electrode, which are inside this closed container. Now, this isn't usually a good idea. Producing gases inside a closed thing is usually not a good idea. But what I've got is a little pipe, which is sending my gas bubbles out here. So I've got this electricity source, and what's going to happen is I'm actually going to start generating those gases when I switch on my power source. So what I'm doing is I'm applying a positive, which is red, and a negative, which is black. And what's actually happening inside there is I've got my two electrodes both producing gases. So these gases are actually being funneled out into this container over here. So what we're going to do is let's just ramp up our production a little bit, and we can actually start seeing that gas is going to start coming out of here, and we're actually catching it in this container over here. So let's just make sure that everything comes out all right. Okay, let's just make sure that everything is sealed. And what we should start noticing is that there's actually bubbles being caught over here. I've put in a little bit of sunlight liquid to catch those bubbles. Now, just remember that these bubbles contain a mixture of hydrogen and oxygen. So I'm hoping that this all works out. I've got a lighter in my pocket here. What we're going to do is just switch off the power for a moment. And what we should hear is a really loud bang. Now, what's inside here is a mixture of hydrogen and oxygen. So what I'm going to do is I'm going to use my ignition source over here. Let's just make sure that it's working. And we should hear an incredibly loud bang. Now, let's just take a look at what's actually happened over there. I've used electricity to split water. I put electricity into the water, which changed electrical energy into chemical potential. Now that oxygen and that hydrogen went out here, and they were trapped together. So they now had that chemical potential energy. What I did was I used a lighter to release that energy. And this is the same energy which actually they used to send rockets into space. Now you can see that tiny little bits of bubbles that made that loud noise. It's absolutely amazing. Okay, guys, please don't do this at home. Because what can happen is this can explode if you're not very careful. That explosion can travel up here, and this is glass, guys. Please don't do this. This is for science teachers. This is for adults. Okay, so if you want to do this, ask your science teacher very, very nicely. Guys, what I'm going to do is let's try to figure out what was going on there, and let's go through an exam question.
That was really awesome, Phil, by the way.
Okay, well, you know, one of many explosions to come, I'm sure. My kids are always asking me, like, let's blow something up.
Let's blow something up.
Absolutely. Okay, well, guys, we've got time for a little bit of an exam question over here. Guys, get onto the page, get our notes, and here they are. So now, here's the exam question which I've selected. These were from the March papers in 2012. So, guys, they're quite useful, especially going through these. Okay, so, guys, please, I need you to be able to go through these and use your redox table. So now it says, which one of the following statements regarding, now here it is, my copper, silver cell. Here's the important bits. Copper and silver are my two metals. And it's a galvanic cell. Guys, this is a spontaneous chemical reaction if it's galvanic. So that's quite important. Let's just grab my pen and let's just make a note on there. So a galvanic cell is spontaneous. Now you might say, okay, well, how do I know if something is spontaneous from looking at this table? Now, if you grab your table and you start to circle copper and silver, just remember that copper and silver galvanic cells will usually have copper ions and silver ions as well. Let's try and figure out what's going on. We've got a few options. We've got silver is formed at the anode, copper is formed at the anode, all of these options, and I'm not actually sure what's going on. So let's try and find out how they're actually positioned on the tables. So if you look on your table, what you'll see is that copper and copper 2+ are positioned above silver. So what you'll notice is that silver is over there and down here. Remember I told you could clean your copper and your silver using lemon juice and some aluminum foil? Now this is the reason why. Now what you'll notice is that if you circle these and if you follow my instructions from earlier, choosing the best one really isn't a problem. So follow your arrows on your redox table, and I want you to think about this. Which one do you think is the best one between copper 2+ and Ag+, between copper metal and silver metal? Now, if you were following the instructions and you looked at the arrows like I told you to, Ag+ is the one to do. What about this other side? Copper is the one to choose because of my arrow. Now, the way to do this is to try and figure out which one is actually reacting. Well, I've got my copper and I know that this is the winner. that means that copper is going to be my reactant and it will change into copper 2+. What about my silver? Silver is going to change into silver metal. Now let's just label these as oxidation or reduction. Now if copper is changing into an ion, that means that it's losing electrons, and that is oxidation. What about this bottom one? Silver changing into silver metal, that must be reduction. Now remember that red or reduction takes place at the cathode. Oxidation at the anode. So what do I know? Copper 2+ is at the anode. What am I making at the cathode? I'm making some silver metal. There it is, and that's my answer. So let's take a look at my potential answers over here. So silver is formed at the anode. No, it's not. I'm making copper 2+. Copper is formed at the anode. No, I'm not. I'm using up the copper metal. Silver is formed at the cathode. Is that correct? Absolutely, guys. Let's just check our last answer. What about copper being formed at the cathode? Absolutely not. So what we're going to find is that copper itself is never being formed. We are making copper 2+. Guys, I hope that you can see, using a couple of really simple steps, the redox table or the standard reduction potentials table can be a very, very simple thing to navigate. I think we've got a little bit of time for one short last question. What do you think, Kat?
I think so. I think we do.
Awesome. Okay. Now, this is getting into the long form of these questions. Now, I particularly like this question. In fact, I put it in a test for my matrix recently. And this one is talking about the refinement of copper using electrolysis. Now, electrolysis, remember, is taking electricity and changing it into chemicals. So let's just take a look. It says the diagram below represents an electrochemical cell used in the refinement of copper. One of the electrodes consists of impure copper. So there we go. That's the one that we're trying to get rid of. And the other of pure copper. So we're trying to just get copper at that one electrode. Now, we've got this power source, and what we've got to do is now we've got to use this power source to change one electrode into ions. So we've got to dissolve the impure, and we've got to make up a new electrode. So we've got to manufacture ions at the one, and we've got to manufacture metal at the other one. So let's go through these questions, and let's see what's going on here. Okay. Now it says, what type of power source is used for the cell? Now this is completely out there. Now it says, write down only AC or DC. Now if you remember from grade 11, AC means alternating current. DC means direct current. Okay, now alternating versus direct current. Oh, how do I know? This doesn't look anything like a generator or a motor. I don't see any split rings or anything like that. How do I deal with this question which says AC or DC? So what I can do is I can say, okay, well, do I need current to flow only in one direction or in both directions? Now, what am I actually trying to do? I'm trying to get one electrode to dissolve and one electrode to build up. What I'm actually finding is that I've got to take electrode P and dissolve it because I was told that one is impure and one is pure. Now, what we've got to do is we've got to change our impure one into a pure. So now information earlier on said that this was the impure electrode and that Q was the pure electrode. How do I get one metal to move into the solution and then move out of the solution again as a pure metal? Well, I've only got to get one reaction to happen. So the impure reaction has got to be from copper into copper 2+, and then the copper 2+ is going to change back into copper on the other electrode. So what's actually happening is I'm dissolving one and I'm building up the other. Oxidation to ions and then reduction to metal again. Now, I don't want the reaction to go backwards and forwards and backwards and forwards. I want it to only go in one direction. And that's why I'm going to use direct current. Direct current is an amazing way to get a reaction to go only in one direction. So it's definitely going to be DC. Let's move on to our next one. It says, give a reason why CuSO4. Now remember, CuSO4 was that blue stuff, that blue salt which I had inside there. Now it says, explain why CuSO4 is dissolved in water before using it inside the cell. Now remember what I said, you need those two metals and you need something in between there. That's called an electrolyte. An electrolyte is made up of ions, which is copper 2+ and SO4 2-. Those are my two ions. Now, these two ions are dissolved in water before using the cell. Now, here's the reason. The reason I need to dissolve them is because when you dissolve ions, you pull them apart. And more than that, you allow them to move. So when I dissolve CuSO4 in this solution, I allow those ions to move and do their job. I need to be able to move the copper somehow. And that's why I need dissolved ions. Dissolved ions can move and conduct electricity. Okay, now into the redox. It tells me, is electrode P the anode or the cathode? Now it says, support your answer by writing down the correct half reaction happening at P. Now, if P is the impure copper, now you've got to ask yourself, do you want copper to change into ions or ions into copper? Now, if P is the impure or the unpure form of copper, I don't want to make more metal on top of it, I want it to dissolve. Now remember what I said about the zinc. When zinc changed into ions, it became soluble. So what you'll find is that copper is going to oxidize into copper 2+ plus 2 electrons. That is oxidation. I'm going to oxidize the impure copper at that electrode. Now that is electrode P, and electrode P therefore must be the anode. That's where oxidation takes place. Now just quickly, writing down the half reaction that happens at electrode Q. Now guys, we're running a little bit short on time, but you can actually imagine that if I put copper into the solution as ions, I need to take the ions out by changing them back into copper and leaving everything else behind. I think that's all we've got time for today.
I think so.
I love this lesson.
I think so, Phil. But hey, at least we had a bit of an explosion there.
We had an explosion, some frights.
I know, some frights there. I know, I got a bit of a fright. Everyone's laughing at me at home like, oh my word, why did you get such a fright? I don't know why I got such a fright, okay? I thought I was braver than that as well. I hope you guys really enjoyed that. Phil, KB is even saying, wow, Phil, I love your experiments. They're always the best.
Thank you so much, KB.
Because he gives us a fright, that's why.
Absolutely. Got to blow stuff up. We've got to compete with Will Smith.
I know, right? We've got to compete with Will Smith. Exactly. I hope you guys have entered that competition. Remember, lines will be open until 12 midnight. So you have all that time to click on that, whatever you have to click on to enter the competition, whether it's enter or not, then hey, click on it. Thank you to Macmillan for sponsoring our show as well. I want to actually read out the names of the winners again. That is Liam Cosgrove, Apiwe Makatini, and Raymondi van der Venter. Well done, guys. Well done for that. Get your 2 tickets and go see Will Smith and Jaden Smith. Thank you for joining us, guys. Bye-bye.